All right, so let's do an example in which we have a coil of wire. So we have a coil of wire here, and we got magnetic field at an angle that is 35 degrees from the plane of the wire. So this is like an oblique view. A side view would be a coil of wire here, and this is coming in at an angle of 35 degrees. So there's the magnetic field. Okay, so things that you need to know here. We need to know the size of the wire. So let's say that the diameter of the wire is going to be, the coil is going to be 14.0 centimeters. Let's say the strength of the magnetic field is going to be 0.303 Tesla. Let's say the coil has 125 turns in it. So that means the wire goes around here 125 times. Okay, and let's say there's a current in that coil of 2.25 amps. And so I want to know what's the torque on that coil as the magnetic field is going through it. Well, we know that torque is going to be equal to mu cross B. Okay, so that means the magnitude of the torque is going to be mu B sine theta. Okay, so now we got to figure out these particular parameters. So first of all, mu. Mu is NIA. Well, N is going to be 125. Okay. I is given. Okay. And likewise, A is pi r squared. So mu equals N times I times pi r squared. Okay, so it'll be 125 times I, which is 2.25 amps, and then we multiply by pi, and then r. Now, I said the diameter was 14 centimeters, so that means r is 7 centimeters. So I've got to put it into meters, so 0.07 meters squared. So mu, which is the magnetic dipole moment, that's going to be 4.33 amp meter squared. Okay. So now, tau, magnitude of the torque, is mu b sine theta. So, magnitude of the torque, mu, 4.33 amp meter squared, times B, 0.303 Tesla, times sine of, now here's the thing, our coil is like this, our B is like that, okay? If we assume that if we look down from this direction, if we look down from that direction, then if we assume that the current is going in a counterclockwise fashion, that means that the area vector is pointed upwards. Now, remember, the mu vector is in the direction of the area vector. So the angle is the angle between the area vector and B. So it's this angle. So it's not 35 degrees. So it's going to be 90 minus 35 degrees. So the angle is going to be 55 degrees. And this is an important point because this is where a lot of students make a mistake, is not getting the correct angle. If you get the right angle, this works fine. If you get the wrong angle, then you get the wrong answer. So it's the angle between the perpendicular to the loop and B, not between the loop and B. So the magnitude of the torque turns out to be 1.07 Newton meters. Okay. Now, if we want to do torque vector, we need to figure out which way it is. So in this case, if it's mu cross B, so side view if it's going so that it's going away from us on this side and towards us on that side, right hand rule, curl your fingers in the direction that the current's going, then mu is in that direction, B is in this direction. So what you do is you point your fingers in the direction of mu, curl them in the direction of B, your thumb points in the direction of the torque. So in this case, the torque is out of the screen. So that means that we can say the torque vector, okay, is going to be 1.07 Newton meters out of the screen, okay. So that means as you're looking at it, it's trying to it's torquing it to try to rotate in that fashion right there. So it's trying to make it rotate counterclockwise as you look at it from the side view.